Okay, so day 2 notes. We're going to start off with just some basics here. We know slope is just rise over run, change in y over change in x. Okay. We're going to do a lot more work with slope later on. Linear equations can be written as point slope form or slope intercept form. You may be more familiar or comfortable with slope intercept form, but in this course, we're going to really steer students towards point slope form. It's the easier one to get to from the information that will be provided for us. And we're going to just try to be comfortable with leaving our equation in point slope form. I mean, we could go to slope intercept form, but we're just doing additional work on the problem that's already finished. So, okay. Parallel lines are where two lines have slopes that are equal to each other. And then two lines are perpendicular if the slopes of the lines if the slopes are opposite reciprocals of each other. So an example of that, if the slope of one line is 3 and the slope of a second line is -1/3, that fulfills the condition of one being the opposite reciprocal of the other. Right? You take that 3, you flip that 3, it becomes 1/3. You change the sign, it becomes -1/3. Okay? So we know that these two lines will intersect at a 90-degree angle. Okay. We also have equations for lines that are vertical and horizontal lines. So vertical line has an equation that takes on the form of x equals. So wherever that vertical line crosses the x-axis, that is the equation for that line. Okay. The horizontal line takes on the form of y equals a constant. So y equals 5 will be a line that goes through the y-intercept of 5. All right, let's look at solving inequalities. So let me go through the steps and then we'll go through this example. Okay. Okay, so the first thing we do is we want to rewrite it as an equation. It makes it easier to work with if we get it down to an equation, because our first goal is to find critical values. So we find critical values by setting both the numerator and denominator equal to 0. We'll make a sign line using critical values, and then we'll test values on that sign line using the inequality. Okay, so let me put this on this. I want to give myself more room here. Okay, so first thing I'm going to do is I'm going to rewrite this as an equation, so I can just kind of have something a little more familiar, because we'll deal with the inequality at the end. And also another thing is, if I can get it down to, if I can get that, get this as an equation set equal to 0, it just makes things a little bit cleaner. So I'm going to subtract this fraction on the right side over to the left. I'm just picking that fraction up and moving it to the left side. Okay. Okay, so now I'm dealing with fractions here. Notice that the fractions do not have the same denominator, so I need to find a common denominator that will have both of these included. So my common denominator is going to be x plus 3 and an x minus 1. So I need to include both to produce common denominator. Once I have common denominators, then I know I can combine two fractions together. So now I got to ask myself, what changes between what changes need to be made from my first old denominator to my new denominator. So I see that the x plus 3 is missing in x minus 1, so that's what's needed to balance the fraction. So I need to multiply the numerator by x minus 1. So if I balance the numerator by x minus 1, then my new numerator is going to be x minus 1 and x plus 5. Okay. My second fraction looks like between my old denominator and my new denominator, this fraction is missing an x plus 3. So I need to balance this numerator for this fraction with x plus 3. Okay, so now the hope is that I can combine these fractions by adding or subtracting the numerators, but now I'm going to spend time to clean up my numerators here. So expand everything out, and be careful, there's that negative there. So I'm going to write this all as one large fraction. I know that these can all combine because now I have matching denominators. Okay, so I'll FOIL all this out here. I'm still going to leave my parentheses for my second fraction because I don't want to lose track of that negative. So I'm going to FOIL this out, and then I'll take care of that negative at the end. Okay, combine like terms. A lot of things will go away nicely for us. All right, so there's my cleaned up version. Next step, I want to look for critical points, critical values. So the way we look for critical values, we're going to set the numerator equal to 0 and the denominator equal to 0. It doesn't mean that we're going to find critical points in both locations, but we're going to start off by looking both locations separately. Okay, so I'll set the numerator equal to 0. Does -8 equals 0 make sense? No, right? So we ignore that. There's no critical points for numerator. We set the denominator equal to 0. X plus 3, x minus 3 equal to 0. That makes sense. We can solve for x. So we have critical points. Okay, so critical values here, critical points. Okay, we're going to place them onto our number line here. So the nice thing about these critical values, it helps separate our potential solution intervals. We know that everything to the left of -3 will have a certain behavior for inequality. We know everything between -3 and 1 will have the same behavior, whether it will all fulfill the inequality or they will all fail the inequality. And we know everything to the right of 1 also are going to be consistent in their representation. So we go back to our inequality here. Okay. and we're going to be testing values against this inequality to see is this interval going to be true, or is it going to be false? Will it fulfill the condition or will it not, right? We know that ultimately we're looking for a set of numbers that fulfills this inequality, that will make this inequality true. Okay, so what we want to do is we want to use test values. Okay, we want to choose values because any number, I can choose any value in this interval, and whatever, if I can test one number, it'll be true for all the numbers here. So I'm going to try to test as small of a number that I can to plug in. So the smallest number I can think of in this interval is -4. The smallest number I can think of that will be easy to test would be 0. The smallest number that I can think of to be easy to test would be 2. Okay, so those numbers I want to test against my inequality. So I'm going back to my original problem. Okay, so I'll start with -4. I'll plug -4 in for x, and I'm just going to see what that gives me and see if I can just determine whether that's a true or false statement. So -4 in for x. So -4 plus 5, that's 1. -4 plus 3 is -1. Okay, is that less than -4 plus 1, which is -3, and -4 minus 1, which is -5. So therefore, is -1 less than 3/5? And that is a true statement, right? We know negative is always going to be less than a positive number. So we know that this is a true statement. I'll put a check mark next to it. We know anything in this interval will be good to go. Any number that I can think of will make that a true statement. Okay, next up, I'll test 0. I'll replace 0 in for all the x's and see if the resulting inequality is true or false. Okay, so 0 for x. 0 plus 1 over 0 minus 1, so 1 over -1. I have 5/3 is less than -1. That is not true, right? 5/3 is not less than -1. So I'll put an x here. That doesn't. We know that that's not going to be part of our solution set. Okay, there's my test case. I'll test 2, and for x. So that's 7 over 5, less than 3 over 1. Okay, so 7/5 is a number slightly larger than 1, and that is less than 3, right? So that's true. We're good to go. So we know our solution set is going to be this interval and this interval. We're going to ignore the red numbers now. These numbers are not going to be part of my answer set. My interval is going to be this entire interval and this interval. Now, the last thing that we have to think about is, what do we do with the critical points? Are the critical points going to be part of our solution, or are they not? So here's a general rule. If your critical point is coming from the denominator, then they will never be part of your solution set. We can always ignore them. Okay, it'll always be open circle. But if your solution set is coming from the numerator, then we got to pay attention to see, is it included in our inequality? If there's a line underneath, then a critical point from the numerator would have to be closed circle. Okay. But in this case, looks like all of our critical points are coming from the denominator. So we know that they will never be part of our solution set. They will be values that are not defined. So we'll always have open circles if they're coming from the denominator. Okay, so we have two solution sets here. Let me highlight them. It's going to be this interval and this interval. So our solution set, we know that these numbers stretch to negative and to positive infinity. So our solution set is from -infinity to -3 with a parentheses, not a bracket. Right? Doesn't include that. We skip the middle interval and we move to the next, the last one. So union 1 to positive infinity. Yes.
Can you repeat what you said about critical points in the numerator?
Right. So if a critical point comes from the numerator, then we have to look at whether there's an equal sign under that inequality. Okay. So for instance, let me just give an example here. Let's say it was 8x over okay, let's say it was that, for instance, right? Let's say the critical point was 0. And because there's a line underneath that inequality, that will tell us that we'll have to shade that in. Okay. But if it was something like this, where the critical point is 0, but there's no line under the inequality, that means we're going to keep that as an open circle. So the only time we close in the circle is if the critical point is from the numerator and there's a line underneath the inequality. Any other situation, your inequality, your critical point is always going to be open circle.
Thank you.
Okay, thanks. Next page. Okay, let me just read through these notes here. Okay, domain is a set of all values where our function is defined. Restrictions can vary depending on the function type. So a rational function, a radical function, trig function, they may all kind of have a different set of domain rules depending on where the graph has vertical asymptotes and where there's a starting or ending point for some of these functions. A range is a set of all values that has been mapped to a value of x in the domain of a function. So your range, typically we're going to have to look at the graph to determine the range. Algebraically, it's easier to determine the domain. Algebraically, it's a little harder to know what the range is without physically graphing. But sometimes we can use transformations to help us with range, but typically we need the help of a graph to usually with range. Okay, some transformation rules here. Let's say we started off with some parent graph that's in the form of y equals f of x. Now that's a very general term there. That f of x could be a polynomial, could be x squared, could be x cubed, could be square root of x. Okay, but just talking from a very general standpoint here. If there's a negative outside of that parent function, what's going to happen is it's going to take that function and it's going to reflect it over the x-axis. Any number any coefficient that's sticking out in front of the parent function, that's going to take that parent function and it's going to stretch it. It's going to be a vertical stretch or compression, depending if that is a value greater than 1 or less than 1. Okay. Anything that is inside the function is going to end up, well, we're not going to worry about that b value. That c value is going to end up shifting the graph either left or right. So you want to think opposites here. If you see a plus, it's going to shift the graph left. If you see a minus, it's going to shift the graph to the right by that many units. Right. Any value that is sitting, that's being added to outside the function, where it's not in a set of parentheses, that's going to take the parent graph and it's going to shift it vertically, either up or down. So if you see a plus, that's going to shift the graph up. If you see a minus a value, it's going to shift the graph by that number of units. Okay, composition of functions. This is where we are inserting a function into another function. So what we're going to do here is we're going to take these f and g, and we're going to find their domain separately before we jump into our composite function. So let's think about 3x squared. So if I have y equals 3x squared, that's a polynomial, that's a parabola. We know the graph is going to stretch infinitely in both directions. There's no breaks in the graph. So our domain is going to be all real numbers. Now, square root of x minus 2, let's talk about the fact that there is a transformation going on involving a parent function. So just for an example here, if I have y equals square root of x, this is what y equals square root of x looks like. It starts at 0, 0, and it's going to open to the right. So if I know that this is the shape of my parent graph, then what do you think the square root of x minus 2 is going to do to that graph? Yeah, shift it to the right. Yeah, you see how it's inside the parentheses, it's inside the function. So it's going to be a left or right movement, and we got to think opposite. So a negative is going to push the graph to the right. So imagine taking this graph and then just shifting the starting point over 2 units. You can get a very rough picture as to what that graph looks like. Now, this is enough for us to determine the domain, right? If you can look at that graph, even though it's not completely accurate in terms of just a very rough sketch, but it's enough for us to determine the domain. The domain is the furthest left to the furthest right of the x values. We can see that it starts at 2 and it shifts over to the right. So now it does hit that value of 2, so we need to make sure we include that as part of our domain. Bracket 2 to positive infinity. Okay, so next we're going to determine that composite function, f of g of x. So we're going to insert the g function into the f function. Let me show you what that looks like. So I'm going to take the g function. Here's, I'm going to put them separately, visually, kind of give you a idea what's going on here. So I'm going to take that square root of x minus 2. See that g of x is inside? I'm going to take everything that's part of my g of x function. I'm going to insert it into the x of my f of x. You see that? So imagine leaving a space where that x was, and then just inserting all that into that space. So if I do that, my f of g of x is going to look like this. 3 parentheses squared with a square root of x minus 2 inside. Okay. Does that make sense? Okay. Now we're going to find the domain of this, but here's the thing: is that there is some restrictions going on here. If you clean this up, you can get the square roots to cancel out, but we want to find the domain before we get there because we want to identify that there is a restriction here, right? That square, if we lose that square root and square, it is the reduced expression, but it doesn't quite give us the full picture as what we're starting with. So here we have that restriction of the x value can't be less than 2, otherwise it's going to all of a sudden become a negative value. So that restriction from the square root of x minus 2 is going to carry over. And we're going to take the more restrictive of the two functions. And also you can tell 2 to infinity must be the domain for this composite function. Example 2, we're going to go the other direction. We're going to find g of f of x. So now I'm going to take my entire f of x function and then put it into my g of x function. Okay, so I'm going to write them out twice and just kind of give you a visual look as to how they're being, how they're worked into each other. So I'm going to take my entire g of x function, insert it into every x of my g of x. but there's only one x, so there's only one substitution that needs to be made. So imagine replacing that x and putting that 3x squared in place of it. All right, does that make sense? Taking the entire inside function and then just fitting it into that space where the x was on the outer function. Okay, now to find a domain, we want to be able to identify what the issue is here. You see how this is inside the square root? So that means there's a built-in restriction with the square root. Okay. So I want to kind of remind us of something here. If I gave you y equals square root of x, we know that there's a restriction, right? We know that that x has to be greater than or equal to 0, right? Because any negatives is just not gonna be part of our real number system. So basically, anything inside the parentheses, inside my radical function, has a restriction of it needs to be greater than or equal to 0. Otherwise, it will not fit. It will not show up on my radical function. So I'm going to take that idea, okay, with the radical and apply it here. You see how this is everything inside the square root must be greater than or equal to 0? Same thing here. Everything inside the square root must be greater than or equal to 0. Otherwise, if that expression produces a negative number, then it can't be part of our graph. It's just not going to show up. So we know that this expression, it must fulfill this condition, because that's just the natural restriction because of the square root. So if we know that this must be true, we can work our way down to solve for x, and we can create intervals just like before and find the range of solutions that will allow us to find the domain. Okay, so just like before when we did the previous inequality problems, I'm going to replace that inequality with an equal sign just to kind of turn our attention to solving for x. I'll add 2 to both sides, divide by 2, divide by 3, take the square roots, plus or minus will show up. Okay, I'm dealing with the inequality, so I need to test using my sign line. Now, square root of 2 over 3, if you plug in the calculator, it's around 0.8 and negative 0.8. So I'm just going to choose values that are nice, easy whole numbers that I can test within each of these 3 subintervals. So -1 is safely to the left of that first critical point. I know 0 is a nice number I can test. And then to the right of square root of 2 over 3, I'm going to test 1. Okay, they're all going to go into this inequality. And whatever makes this true, I know will be part of my domain. If it doesn't make it true, then I know it can't be part of my domain. Okay, so I'm going to test each point at a time. If it passes the test, that means everything in this interval is going to pass. If it fails the test, that means every number in this interval is going to fail. Okay, so there's my test number here. If I plug -1 in for x, 3 times -1 squared, that's 3. 3 minus 2 is 1. 1 is greater than 0. That's true. I get a positive number. That's true. I know I'm going to keep that interval. Okay. If I test 0, 0 for x, I get 3 times 0, 0. 0 minus 2 is negative. -2 is not greater than equal to 0. So we know that negative is going to fail. And then test 1 again. 1 in for x. 3 times 1 squared is 3. 3 minus 2 is 1. 1 is greater than 0. That's true. Okay, and this goes back to, I think question that I think Michael was asking, that how do we know what to do with these critical points? Notice how we found those critical points from the numerator, right? There was no denominator, so we know that there's a chance that we're going to have to include those critical points. So I'm going to put circles around it. Now our next decision is based off our inequality. You see how there's a line underneath there? So that tells us it's coming from the numerator, and that's greater than or equal to 0. That equal sign tells us that we're going to shade these in. Those critical points is part of our solution. So here we have our 2 intervals, and that will create the domain for our composite function. So bracket, union, okay, any questions? Okay, tomorrow we'll finish these notes. We're not going to have a test on chapter P, but we're really, tomorrow really want to focus on the topics that will be really useful and helpful as we prepare for Unit 1 and Unit 2. Guys, a couple of things here, announcements. If you haven't signed up for my Remind, make sure you do that. It's on my syllabus. Okay. Second thing is your homework exercise problems are in your packet, but I photocopied all the problems from the exercise. You're not going to do all of them, right? You're only going to do the ones that are specified in your calendar. Okay. So your calendar has the page number. Okay. And it'll identify the questions. So I'll check homework on Monday for P1, P2, and P3. So hopefully you're able to kind of chip away at it, do a little bit each day so that you're not waiting until Sunday to do all the homework problems. Okay. Feel free to send me a text reminder if something doesn't make sense. I worked out all the homework problems on the chapter 1 page, chapter P page. So it should be under today's date or yesterday's date.
Good afternoon, Milton Eagle. Students, if you have lunch/study hall during course, please report to your study hall class when the bell rings at 11:30. 9th and 10th graders have lunch A, 11th and 12th graders